powering off.
An example, and the third is self-attention with some math, intuition, and code. So stay tuned. This here is a recurrent neural network that's rolled out. And X's are the inputs, the O's are the outputs, the H's are the hidden states, and the Y is the training label. Recurrent neural networks used to be the state of the art for sequence-to-sequence modeling. Sequences can be an ordered set of tokens, which could be like a set of words to form a sentence, for example. And so these recurrent neural networks in many applications of natural language processing were the state of the art for sequence-to-sequence tasks. However, they suffer from two main disadvantages. So the first is that they're slow. We need to feed these inputs one at a time in order to generate the outputs sequentially one at a time. Also, their training algorithm is pretty slow too. We use a truncated version of backpropagation to train them, and the algorithm is called truncated backpropagation through time. But probably a more pressing Hello everyone, and welcome to another episode of Code Emporium, where we're going to talk about transformer neural networks. And in this video specifically, we're going to go through some intuition, some code, and some math of how to deal with attention and transformers step by step. So we're going to divide this video into three parts. So first we'll start with the motivation for why we need attention. The second is the transformer architecture and walking through an example. And the third is self-attention with some math, intuition, and code. So
Hi. Yes,
Hi everyone. Welcome to CS25 Transformers United V2. This was a course that was held at Stanford in the winter of 2023. This course is not about robots that can transform into cars, as this picture might suggest. Rather, it's about deep learning models that have taken the world by the storm and have revolutionized the field of AI and others. Starting from natural language processing, transformers have been applied all over, from computer vision, reinforcement learning, biology, robotics, etc. We have an exciting set of videos lined up for you, with some truly fascinating speakers give talks presenting how they're applying transformers to the research in different fields and areas. We hope you'll enjoy and learn from these videos. So without any further ado, let's get started. This is a purely introductory lecture, and we'll go into the building blocks of transformers. So first, let's start with introducing the instructors.
So for me, I'm currently on a temporary deferral from the PhD program, and I'm leading AI at a robotics startup, Collaborative Robotics. We're working on some general purpose robots, somewhat like a support. And yeah, I'm very passionate about robotics and building efficient learning algorithms. My research interests are in reinforcement learning, computer vision, and modeling, and I have a bunch of publications in robotics, autonomous driving, and other areas. My undergrad was at Cornell. It's someone's book Cornell. So nice to meet you. Cool.
So I'm Steven, currently first year CSP speaker. Previously did my master's at CMU and undergrad at Waterloo. Mainly into NLP research, anything involving language and text. But more recently, I've been getting more into computer vision as well as multimodal. And just some stuff I do for fun. A lot of music stuff, mainly piano. Some self-promo, but I post a lot on my Insta, YouTube, and TikTok. So if you guys want to check it out. My friends and I are also starting a Stanford Piano Club. So if anybody's interested, feel free to email or DM me for details. Other than that, martial arts, bodybuilding, and huge fan of K-dramas, anime, and occasional gamer.
Okay, cool. Yeah, so my name's Rylan. Instead of talking about myself, I just want to very briefly say that I'm super excited to take this class. I took it the last time it was offered. Sorry, to teach this class. Excuse me. I took it the last time it was offered. I had a bunch of fun. I thought we brought in a really great group of speakers last time. I'm super excited for this offering. And yeah, I'm thankful you're all here, and I'm looking forward to a really fun quarter together. Thank you.
Yeah, so fun fact, Rylan was the most outspoken student last year. And so if someone wants to become instructor next year, you know what to do. Okay, cool. Let's see. Okay. Yeah. So what we hope you will learn in this class is, first of all, how do transformers work? How they're being applied, just definitely. And nowadays, like, we are pretty much using them everywhere in AI, machine learning. And what are some new interesting directions of research in these topics? Cool. So this class is just introductory. So we're just talking about the basics of transformers, introducing them, talking about the self-attention mechanism on which they're founded, and we'll do a deep dive more on like models like BERT, GPT, stuff like that. So great, happy to get started. Okay, so let me start with presenting the attention timeline. Attention all started with this one paper, Attention is All You Need, by Baswani et al. In 2017. That was the beginning of transformers. Before that, we had the prehistoric era where we had models like RNNs, LSTMs, and simple attention mechanisms that didn't work or scale that up. Starting 2017, we saw this explosion of transformers into NLP, where people started using it for everything. I even heard this quote from Google: "It's like our performance increased every time we fired our linguist." For the first 2018, after 2018 to 2020, we saw this explosion of transformers into other fields, where people started using it for everything. I even heard this quote from Google: "It's like our performance increased every time we fired our linguist." Everything. I even heard this quote from Google: "It's like our performance increased every time we fired our linguist." Performance increased every time we fired our linguist. For the first 2018, after 2018 to 2020, we saw this explosion. Our performance increased every time we fired our linguist. For the first 2018, after 2018 to 2020, we saw this explosion of transformers into other fields like vision, bunch of other stuff, and like biology, AlphaFold. And in last year, 2021 was the start of the generative era, where we got like a lot of generative modeling. Started like models like Codex, GPT, DALI, Stable Diffusion. So a lot of like things happening in generative modeling, and so we started scaling up in AI. And now the present. So this is 2022 and like the start of 2023, and now we have models like ChatGPT, Whisper, a bunch of others, and we are like scaling onwards without slowing down. So that's great. So that's the future. So going more into this, so once there were RNNs, so we had sequence-to-sequence models, LSTMs, GIUs. What worked here was that they were good at encoding history, but what did not work was they didn't encode long sequences, and they were very bad at encoding context. So consider this example. Consider trying to predict the last word in the text. I grew up in France, ... I speak fluent dash. Here, you need to understand the context for it to predict French, and like attention mechanism is very good at that. Whereas if you're just using LSTMs, it doesn't work that well. Another thing transformers are good at I speak fluent. What worked here was that they were good at encoding history, but what did not work was they didn't encode long sequences, and they were very bad at encoding context. So consider this example. Consider trying to predict the last word in the text, I grew up in France, ... I speak fluent dash. Here, you need to understand the context for it to predict French. And like attention mechanism is very good at that. Whereas if you're just using LSTMs, it doesn't work that well. Another thing transformers are good at is more based on content is like also context prediction is like finding attention maps. If I have something like a word like it, what noun does it correlate to? And we can give like a probability attention on what are the possible activations. And this works better than existing mechanisms. Okay. So where we were in 2021, we were on the verge of takeoff. We were starting to realize the potential of transformers in different fields. We solved a lot of long sequence problems like protein folding, AlphaFold, offline RL. We started to see zero-shot generalization. We saw multimodal tasks and applications like generating images from language. So that was DALI. Yeah, and it feels like Asian, but was only like 2 years ago. And this is also a talk on transformers that you can watch in video. Yeah, cool. And this is where we were going from 2021 to 2022, which is we have gone from the verge of taking. Yeah.
Was able to solve long sequence problem. Oh no. So long sequence problem. Example protein problem. Oh, line order. Okay. Few short and zero short generalization.
Cool. And this is where we were going from 2021 to 2022, which is we have gone from the verge of taking off to actually taking off. And now we are seeing unique applications in audio generation, art, music, storytelling. We are starting to see reasoning capabilities like common sense, logical reasoning, mathematical reasoning. We are also able to now get human enlightenment and interaction. We're able to use reinforcement learning and human feedback. That's how ChatGPT is trained to perform really good. We have a lot of mechanisms for controlling toxicity, bias, and ethics now, and a lot of developments in other areas like different models. Cool. So the future is a spaceship, and we're all excited about it. And there's a lot more applications that we can enable. And it'll be great if you can see transformers also work here. One big example is video understanding and generation. That is something that everyone is interested in, and I'm hoping we'll see a lot of models in this area this year. Also finance, business. I'll be very excited to see GPT author novel, but we need to solve very long sequence modeling, and most transformer models are still limited to like 4,000 tokens or something like that. So we need to do make them generalize much more better on long sequences. We also want to have generalized agents that can do a lot of multitask, multi-input predictions like Gato, and so I think we will see more of that too. And finally, we also want to see predictions like Gato, and so I think we will see more of that too. And finally, we also want domain-specific models. So you might want like a GPT model that's good at like maybe like your health. So that could be like a doctor good at what we normally consult an expert with. There's still a lot of missing ingredients to make this all successful. The first of all is external memory. We are already starting to see this with models like ChatGPT, where the interactions are short-lived. There's no long-term memory, and this is something we want to fix. Second is reducing the computation complexity. So attention mechanism is quadratic over the sequence length, which is slow, and we mechanism is quadratic over the sequence length, which is slow, and we want to reduce it or make it faster. Another thing we want to do is we want to enhance the controllability of these models. Like a lot of these models can be stochastic, and we want to be able to control what sort of outputs we get from them. And you might have experienced with ChatGPT, if you just refresh, you get like different output each time, but you might want to have a mechanism that controls what sort of things you get. And finally, we want to align our state-of-art language models with how the human brain works. And we are seeing.
Hey, hi. Yes, I'm excited to be here. I live very nearby, so I got the invites to come to class, and I was like, okay, I'll just walk over. But then I spent like 10 hours on the slides, so it wasn't as simple. I live very nearby, so I got the invites to come to class, and I was like, okay, I'll just walk over. But then I spent like 10 hours on the slides, so it wasn't as simple. Okay, I'll just walk over. But then I spent like 10 hours on the slides, so it wasn't as simple. So yeah, I want to talk about transformers. I'm going to skip the first two over there. We're not going to talk about those. We're going to talk about that one, just to simplify the lecture since we don't have time. Okay, so I wanted to provide a little bit of context of why does this transformers class even exist. So a little bit of historical context. I feel like Bilbo over there. I joined like telling you guys about this. I don't know if you guys saw Lord of the Rings. And basically, I joined AI in roughly 2012 in full force, so maybe a decade ago. And back then, you wouldn't even say that you joined AI, by the way. That was like a dirty word. Now it's okay to talk about, but back then, it was not even deep learning. It was machine learning. That was the term you would use if you were serious. But now AI is okay to use, I think. So basically, do you even realize how lucky you are potentially entering this area in roughly 2023? So back then, in 2011 or so, when I was working specifically on computer vision, your pipelines looked like this. So you wanted to classify some images. You would go to a paper, and I think this is representative. You would have 3 pages in the paper describing all kinds of a zoo of kitchen sink of different kinds of features, descriptors. And you would go to a poster session and in computer vision conference, and everyone would have their favorite feature descriptor that they're proposing. And it was totally ridiculous. And you would take notes on like which one you should incorporate into your pipeline, because you would extract all of them, and then you would put an SVM on top. So that's what you would do. So there's 2 pages. Make sure you get your sparse histograms, your SSIMs, your color histograms, textons, tiny images, and don't forget the geometry-specific histograms. All of them have basically complicated code by themselves. So you're collecting code from everywhere and running it, and it was a total nightmare. On top of that, it also didn't work. So this would be, I think, representative prediction from that time. You would just get predictions like this once in a while, and you'd be like, you just shrug your shoulders like that just happens once in a while. Today, you would be looking for a bug. And worse than that, every single sort of field of every single chunk of AI had their own completely separate vocabulary that they work with. So if you go to NLP papers, those papers would be completely different. So you're reading the NLP paper, and you're like, what is this part of speech tagging, morphological analysis, syntactic parsing, co-reference resolution? What is MP, BT, JJ? And you're confused. So the vocabulary and everything was completely different, and you couldn't read papers, I would say, across different areas. So now that changed a little bit starting 2012 when Alex Krizhevsky and colleagues basically demonstrated that if you scale a large neural network on large data set, you can get very strong performance. And so up till then, there was a lot of focus on algorithms, but this showed that actually neural nets scale very well. So you need to now worry about compute and data, and if you scale it up, it works pretty well. And then that recipe actually did copy paste across many areas of AI. So we started to see neural networks pop up everywhere since 2012. So we saw them in computer vision and NLP and speech and translation in RL and so on. So everyone started to use the same kind of modeling toolkit, modeling framework. And now when you go to NLP and you start reading papers there in machine translation, for example, this is a sequence to sequence paper, which we'll come back to in a bit. You start to read those papers and you're like, okay, I can recognize these words, like there's a neural network, there's a parameter, there's an optimizer, and it starts to read like things that you know of. So that decreased tremendously the barrier to entry across the different areas. And then I think the big deal is that when the transformer came out in 2017, it's not even that just the toolkits and the neural networks were similar, it's that literally the architectures converged to like one architecture that you copy paste across everything seemingly. So this was kind of an unassuming machine translation paper at the time proposing the transformer architecture, but what we found since then is that you can just basically copy paste this architecture and use it everywhere. And what's changing is the details of the data and the chunking of the data and how you feed it in. And that's a caricature, but it's kind of like a correct first order statement. And so now papers are even more similar looking because everyone just the data and use it everywhere. And what's changing is the details of the data and the chunking of the data and how you feed it in. And that's a caricature, but it's kind of like a correct first order statement. And so now papers are even more similar looking because everyone's just using transformer. And so this convergence was remarkable to watch and unfolded over the last decade, and it's pretty crazy to me. What I find kind of interesting is I think this is some kind of a hint that we're maybe converging to something that maybe the brain is doing, because the brain is very homogeneous and uniform across the entire sheet of your cortex. And okay, maybe some of the details are changing, but those feel like hyperparameters of like a transformer. But your auditory cortex and your visual cortex and everything else looks very similar. And so maybe we're converging to some kind of a uniform, powerful learning algorithm here, something like that. I think is kind of interesting. Exciting. Okay, so I want to talk about where the transformer came from briefly, historically. So I want to start in 2003. I like this paper quite a bit. It was the first sort of popular application of neural networks to the problem of language modeling. So predicting, in this case, the next word in a sequence, which allows you to build generative models over text. And in this case, they were using multi-layer perceptron. So a very simple neural net. The neural nets took 3 words and predicted the probability distribution for the 4th word in a sequence. So this was well and good at this point. Now, over time, people started to apply this to machine translation. So that brings us to a very simple neural net. The neural nets took 3 words and predicted the probability distribution for the 4th word in a sequence. So this was well and good at this point. Now, over time, people started to apply this to machine translation. So that brings us to sequence paper from 2014 that was pretty influential. And the big problem here was, okay, we don't just want to take 3 words and predict the 4th. We want to predict how to go from an English sentence to a French sentence. And the key problem was, okay, you can have arbitrary number of words in English and arbitrary number of words in French. So how do you get an architecture that can process this variably sized input? And so here they use a LSTM, and there's basically 2 chunks of this which are covered by the by this. But basically, you have an encoder LSTM on the left, and it just consumes one word at a time and builds up a context of what it has read. And then that acts as a conditioning vector to the decoder RNN or LSTM that basically goes chunk for the next word in the sequence, translating the English to French or something like that. Now, the big problem with this that people identified, I think, very quickly and tried to resolve is that there's what's called this encoder bottleneck. So this entire English sentence that we are trying to condition on is packed into a single vector that goes from the encoder to the decoder. And so this is just too much information to potentially maintain in a single vector, and that didn't seem correct. It acts as a conditioning vector to the decoder RNN. Get an architecture that can process this variably sized input. And so here they use a LSTM, and there's basically 2 chunks of this which are covered by this. But basically, you have an encoder LSTM on the left, and it just consumes one word at a time and builds up a context of what it has read. And then that acts as a conditioning vector to the decoder RNN or LSTM that basically goes chunk for the next word in the sequence, translating the English to French. Something like that. Now, the big problem with this that people identified, I think, very quickly and tried to resolve is that there's what's called this encoder bottleneck. So this entire English sentence that we are trying to condition on is packed into a single vector that goes from the encoder to the decoder, and encoder bottleneck. So this entire English sentence that we are trying to condition on is packed into a single vector that goes from the encoder to the decoder. And so this is just too much information to potentially maintain in a single vector, and that didn't seem correct. And so people were looking around for ways to alleviate the encoder bottleneck, as it was called at the time. And so that brings us to this paper, Neural Machine Translation by Jointly Learning to Align and Translate. And here, just quoting from the abstract, in this paper, we conjectured that the use of a fixed length vector is a bottleneck in improving the performance of the basic encoder-decoder architecture, and proposed to extend this by allowing the model to automatically soft search for parts of the source sentence that are relevant. Encoder bottleneck, as it was called at the time. And so that brings us to this paper, Neural Machine Translation by Jointly Learning. And so this is just too much information to potentially maintain in a single vector, and that didn't seem correct. And so people were looking around for ways to alleviate the encoder bottleneck, as it was called at the time. And so that brings us to this paper, neural goes from the encoder to the decoder. And so this is just too much information to potentially maintain in a single vector, and that didn't seem correct. And so people were looking around for ways to alleviate the encoder bottleneck, as it was called at the time. And so that brings us to this paper, Neural Machine Translation by Jointly Learning to Align and Translate. And here, just quoting from the abstract, in this paper, we conjectured that the use of a fixed length vector is a bottleneck in improving the performance of the basic encoder-decoder architecture, and proposed to extend this by allowing the model to automatically soft search for parts of the source sentence that are relevant to predicting a target word. In this paper, we conjectured that the use of a fixed length this paper, Neural Machine Translation by Jointly Learning to Align and Translate. And here, just quoting from the abstract, in this paper, we conjectured that the use of a fixed length vector is a bottleneck in improving the performance of the basic encoder-decoder architecture, and proposed to extend this by allowing the model to automatically soft search for parts of the source sentence that are relevant to predicting a target word, without having to form these parts or heart segments explicitly. So this was a way to look back to the words that are coming from the encoder, and it was achieved using this soft search. So as you are decoding in the words here, while you are decoding them, you are allowed to look back at the words at the encoder via this soft attention mechanism proposed in this paper. And so this paper, I think, is the first time that I saw basically attention. So your via the soft attention mechanism encoding them. You're allowed to look back at the words at the encoder via the soft attention mechanism. Proposed in this paper. And so this paper, I think, is the first time that I saw basically attention. So your context vector that comes from the encoder is a weighted sum of the hidden states of the words in the encoding. And then the weights of this sum come from a softmax that is based on these compatibilities between the current state as you're decoding and the hidden states generated by the encoder. And so this is the first time that really you start to like look at it, and this is the current modern equations of the attention. And I think this was the first paper that I saw it in. It's the first time that there's word attention used, as far as I know. And so this paper, I think, is the first time that I saw basically attention that are coming from the encoder. And it was achieved using this soft search. So as you are decoding in the words here, while you are decoding them, you are allowed to look back at the words at the encoder via this soft attention mechanism proposed in this paper. And so this paper, I think, is the first time that I saw basically attention. So your context vector that comes from the encoder is a weighted sum of the hidden states of the words in the encoding. Of the hidden states of the words in the encoding. And then the weights of this sum come from a softmax that is based on these compatibilities between the current state as you're decoding and the hidden states generated by the encoder. And so this is the first time that really you start to like look at it, and this is the current modern equations of the you're decoding and the hidden states is based on these compatibilities between the current state as you're decoding and the hidden states generated by the encoder. On these compatibilities between the current state come from a softmax that is based on these compatibilities between the current state as you're decoding and the hidden that is based on these compatibilities between the current state as you're decoding and the hidden states generated by the encoder. And so this is the first time that really you start to like look at it, and this is the current modern equations of the attention. And I think this was the first paper that I saw it in. It's the first time that there's a word attention used, as far as I know, to call this mechanism. So I actually tried to dig into the details of the history of the attention. So the first author here, Dimitri, I had an email correspondence with him, and I basically sent him an email. I'm like, Dimitri, this is really interesting. Transformers have taken over. Where did you come up with the soft attention mechanism that ends up being the heart of the transformer? And to my surprise, he wrote me back this like massive email, which was really fascinating. So this is an excerpt from that email. So basically, he talks about how he was looking for a way to avoid this bottleneck between the encoder and decoder. He had some ideas about cursors that traversed the sequences that didn't quite work out. And then here, so one day I had this thought that it would be nice to enable the decoder RNN to learn to search where to put the cursor in the source sequence. This was sort of inspired by translation exercises that learning English in my middle school involved. You gaze shifts back and forth between source and target sequence as you translate. So literally, I thought this was kind of interesting that he's not a native English speaker. And here that gave him an edge in this machine translation that led to attention and then led to transformer. So that's really fascinating. I expressed the soft search as softmax and then weighted averaging of the binary states. And basically, to my great excitement, this worked from the very first try. So really, I think, interesting piece of history. And as it later turned out, the name of RNN search was kind of lame. So the better name attention came from Joshua on one of the final passes as they went over the paper. So maybe attention is all you need would have been called like RNN search is all you need. But we have Yoshua Bengio to thank for a little bit of a better name, I would say. So apparently that's the history of this, which I thought was interesting. Okay, so that brings us to 2017, which is attention is all you need. So this attention component, which in Dimitri's paper was just like one small segment, and there's all this bidirectional RNN and decoder, and this attention only paper is saying, okay, you can actually delete everything. Like what's making this work very well is just the attention by itself. And so delete everything, keep attention. And then what's remarkable about this paper actually is usually you see papers that are very incremental. They add like one thing and they show that it's better. But I feel like attention is all you need was like a mix of multiple things at the same time. They were combined in a very unique way and then also achieved a very good local minimum in the architecture space. And so to me, this is really a landmark paper that is quite remarkable. And I think had quite a lot of work behind the scenes. So delete all the RNN, just keep attention. Because attention operates over sets, and I'm going to go into this in a second, you now need to positionally encode your inputs because attention doesn't have the notion of space by itself. They equal, oops, I have to be very careful. They equal, oops, I have to they equal, oops, I have to be very careful. They adopted this residual network structure from ResNets. They interspersed attention with multi-layer perceptrons. They used layer norms, which came from a different paper. They introduced the concept of multiple heads of attention that were applied in parallel. And they gave us, I think, like a fairly good set of hyperparameters that to this day are used. So the expansion factor in the multi-layer perceptron goes up by 4x. And we'll go into like a bit more detail. And this 4x has stuck around. And I believe like there's a number of papers that try to play with all kinds of little details of the transformer, and nothing like sticks because this is actually quite good. The only thing to my knowledge that stuck, that didn't stick, was this reshuffling of the layer norms to go into the pre-norm version, where here you see the layer norms are after the multi-headed attention or feed forward. They just put them before instead. So just reshuffling of layer norms, but otherwise the GPTs and everything else that you're seeing today is basically the 2017 architecture from 5 years ago. And even though everyone is working on it, it's proven remarkably resilient, which I think is really interesting. There are innovations that I think have been adopted also in positional encodings. It's more common to use different rotary and relative positional encodings and so on. So I think there have been changes, but for the most part, it's proven very resilient. So really quite an interesting paper. Now I wanted to go into the attention mechanism. And I think I sort of like the way I interpret it is not similar to the ways that I've seen it presented before. So let me try a different way of like how I see it. Basically, to me, attention is kind of like the communication phase of the transformer. And the transformer interleaves two phases, the communication phase, which is the multi-headed attention, and the computation stage, which is this multi-layer perceptron or p-TWRP. So in the communication phase, it's really just a data-dependent message passing on directed graphs. And you can think of it as, okay, forget everything with machine translation and everything. We have directed graphs at each node. You are storing a vector. And then let me talk now about the communication phase of how these vectors talk to each other in this directed graph. And then the compute phase later is just the multi-layer perceptron, which then basically acts on every node individually. But how do these nodes talk to each other in this directed graph? So I wrote like some simple Python I wrote this in Python basically to create one round of communication of using attention as the message passing scheme. So here, a node has this private data vector, as you can think of it as private information to this node, and then it can also emit a key, a query, and a value, and simply that's done by linear transformation from this node. So the key is what are the things that I am. The query is what are the things that I'm looking for. The key is what are the things that I have, and the value is what are the things that I will communicate. And so then when you have your graph that's made up of nodes and some random edges, when you actually have these nodes communicating, what's happening is you loop over all the nodes individually in some random order, and you're at some node, and you get the query vector Q, which is I'm a node in some graph, and this is what I'm looking for. And so that's just achieved via this linear transformation here. And then we look at all the inputs that point to this node, and then they broadcast what are the things that I have, which is their keys. So they broadcast the keys. I have the query. Then those interact by dot product to get scores. So basically, simply by doing dot product, you get some kind of a unnormalized weighting of the interestingness of all of the information in the nodes that point to me and to the things I'm looking for. And then when you normalize that with softmax, so it just sums to 1, you basically just end up using those scores, which now sum to 1 in our probability distribution, and you do a weighted sum of the values to get your update. So I have a query, they have keys, dot products to get interestingness or like affinity, softmax to normalize it, and then weighted sum of those values flow to me and update me. And this is happening for each node individually, and then we update at the end. And so this kind of a message passing scheme is kind of like at the heart of the transformer, and happens in a more vectorized, batched way that is more confusing, and is also interspersed with layer norms and things like that to make the training behave better. But that's roughly what's happening in the attention mechanism, I think, on a high level.
Rated some. Okay. Just ఏంది ఇది ఫస్ట్ మా పేపర్ చదవడానికి ఎందుకు రాస్తారు కోడ్ అర్థమవుతలేదు. అయితే ఫస్ట్ అట్లీస్ట్ బేసిక్ అర్థం చేసుకుందాం ఎట్లా పనిచేస్తుందని చెప్పని చూసి